So as I was saying, for those who are at the math conversations on Wednesday, you'll be pleased to see that Robert Young has returned, and he will be speaking on embeddings of the Heisenberg group and the sparsest cut problem. Okay, go ahead, Robert.
Thanks. Okay, so this has been this is a really stressful time.
Robert, can you
yeah,
hear?
I'm here. Can you hear me? Okay.
We can.
This has been a really stressful time. My attention span has gone down precipitously in the past couple of weeks. So I figure I'll start just by giving a quick summary of the talk, so that you know what to pay attention for later on. But basically, the idea is that Asaf and I got interested in this problem because of a question from computer science about the sparsest cut problem. So the sparsest cut problem is a classic computer science problem about cutting a graph into two pieces. And it is NP hard. It's hard to solve exactly. But there are approximate algorithms for it. There are algorithms that run in polynomial time that find approximate solutions. And those algorithms, the accuracy of those algorithms depends on how well certain metric spaces embed in the Banach space L1. In particular, how well the Heisenberg group embeds in the Banach space L1. And so we got interested in embeddings of the Heisenberg group. And well, how well does the Heisenberg group embed in L1? It's known to embed poorly in Euclidean space, in Rn. And the reason it embeds poorly in Euclidean space has to do with differentiability. Lipschitz maps from the Heisenberg group to Rn are differentiable almost everywhere, which means that locally, on small scales, they're close to linear. In fact, on small scales, they're close to homomorphisms. But there aren't any good homomorphisms from the Heisenberg group to Rn. They all collapse the center of the group. And so there aren't any by Lipschitz maps from the Heisenberg group to Rn because they have to collapse the center of the group. That argument doesn't quite work in L1, but Kiger, Kleiner, and Knorr came up with an argument to prove a similar sort of differentiability for maps from the Heisenberg group to L1 based on rectifiability, based on how flat surfaces in the Heisenberg group are. And so what Asaf and I did was we found bounds on embeddings of the Heisenberg group to L1 by bounding how flat surfaces in the Heisenberg group can be. The good news is that if you have a surface in the Heisenberg group, you can decompose it. You can break it down into pieces called intrinsic Lipschitz graphs, which are reasonably nice. The bad news is that they're not that nice. This is an example of an intrinsic Lipschitz graph. It can still be very rough. It can still be very far from flat. But you can do analysis to show that even though this intrinsic Lipschitz graph is very messy, it still has it's still close to flat on average, and so that's that's what we did. And so the upshot of this talk is basically that, well, the sparsest cut problem, this problem in computer science, is related to metric embeddings from the Heisenberg group into L1. Embeddings from the Heisenberg group into L1 are controlled by rectifiability, by how flat surfaces in the Heisenberg group are. And we can bound that rectifiability by doing analysis and geometry in the Heisenberg group. So that's the short version of this talk. And so now let me try to go through that a little in a little bit more detail. So are there any questions about anything so far, or anything people want to ask? Okay, so let's do this. So let's start. Let's start with the computer science. Let's start with the sparsest cut problem. So the sparsest cut problem, like I said, is a problem about cutting a graph into two pieces. The input is a graph, and you want to find the best way of the best cut of that graph, the sparsest cut of that graph. So a cut is just a way of dividing the graph into two pieces, and so we'll represent a cut just by some subset of the vertices. And the sparsest cut problem asks us to find phi of g, which is the minimum sparsity of a cut, where the sparsity of a cut S is defined as the number of edges between S and S complement, the number of edges that cross the boundary of the cut, divided by the number of vertices in S times the number of vertices in S complement, the maximum number of vertices that could cross the cut. So here's an example of a graph. In this case, we have 7 vertices, but you can see that they're divided into a click of 4 and a click of 3, and then we have 2 edges between them. And so the best way to cut this graph into 2 pieces is to just separate those clicks, in which case you have 2 edges that cross the boundary of the cut. Out of a possible 4 times 3 is 12 possible edges between the cut. And so you have sparsity of 1/6. Now, this problem, I've stated it as a graph problem, but you can turn it into a matrix problem. Here's my same graph, but here I've written the adjacency matrix of that graph. This is just a matrix with 1 row and 1 column for every vertex of the graph, and then a 0 or a 1 in each entry, depending on whether there's an edge between those 2 vertices or not. If I have a cut, if I have some subset of the vertices, then that gives me a 2x2 block decomposition of the matrix. And then I can define the sparsity of that cut, or I can calculate the sparsity of that cut in terms of the number of ones in the off-diagonal blocks of that decomposition. So the sparsity of S is equal to sum over I in S, J naught in S of Cij, divided by the sum over I in S, J naught in S of 1. And the advantage of stating this problem as a matrix problem rather than a graph problem is that we can generalize it. We don't have to use an adjacency matrix for this matrix here. We don't have to use the all ones matrix in the denominator here. We can replace those with 2 arbitrary matrices. Typically, these are called C and D for capacity and demand. And given 2 such matrices, let's make them symmetric n by n matrices with non-negative entries. We define the sparsity of a cut as the sum over I in S, J in S complement of Cij over the sum over I in S, J naught in S of Dij. And again, we try to minimize over all the possible cuts. And if Cij is the adjacency matrix of some graph and Dij is the all ones matrix, this is exactly the same as what we did before. But in general, this is, a more general problem. This is actually a really nice general framework for problems about taking some collection of things and splitting them into 2. This shows up a lot, for instance, in divide and conquer algorithms, where you have one big problem, and then you solve it by cutting it into 2 problems, and then cutting those into smaller problems, and cutting those into smaller problems, and so on, until the problems are small enough to solve, and then you can combine the solutions of the small problems to get a solution of your original big problem. How well that works can depend on how exactly you split your problem up into halves. And so if you can write the quality of a splitting in terms of a capacity matrix and a demand matrix, then you can use the sparsest cut problem in your divide and conquer algorithm. The quality of your divide and conquer problem algorithm might depend on how well you can solve the sparsest cut problem. Unfortunately, the sparsest cut problem is hard. It's NP hard. But there are ways to solve it approximately. There are polynomial times to approximate phi of CD based on metric embeddings. So let me explain this. So the idea is that we can use metrics, we can use geometry to construct relaxations of the problem. What that means is that, well, our original problem, we were minimizing over subsets of the set of numbers between 1 and n. That turns out to be a difficult set to work with. Very often we can expand this set and get an easier minimization problem. So rigorously, we'll define the set of cut metrics to be semi-metrics of the form dsij is characteristic function of s at I minus the characteristic function of s at j. So this is just, this is 1 if one of them is, if I is in the set and j is not, or vice versa, and it's 0 if I and j are both in the set or both not in the set. This, we can think of it as a subset of the n by n matrices, let's call it C. And then we can define, if I have some set of n by n matrices, which I call K, I can define a corresponding relaxation, which is I minimize the sparsity of, I minimize sparsity over elements of K. So, which is to say, I minimize the fraction sum over all I and j of Cij Mij over Cij over the sum over I and j of Dij Mij. If M is a cut metric, this is exactly the sparsity that we saw before. But if M is not a cut metric, then it's something different. So what I mean by that, so for the cut metrics, this is exactly what we saw before. But if K is something a little more general, then this could be smaller than the sparsity over, or than the minimum over the cuts, because we're expanding the set that we're minimizing over. The trick here, what we want is we would like to find some K so that on one hand, it's easy to compute the minimum over all K of this quantity. But on the other hand, we want that minimum to be close to phi. We want this to be a good approximation of the set of cut metrics. And there's a sort of tension, there's a tension between those two goals, because on one hand, for this minimum to be close to the minimum over the cut metrics, that means that we want this set of matrices to be close to the set of cut metrics. But on the other hand, the set of cut metrics is kind of hard to minimize over. In order to make this minimum easy to compute, it helps to make this set as big as possible. So for instance, if we were minimizing over all the matrices instead of just all the cut matrices, this quotient, this minimum would be trivial to compute, but it would be very far away from, it wouldn't have anything to do with the actual sparsest cut. Okay? Is this okay so far? Are there any questions about anything so far? Okay. So the way that geometry comes in here is that it turns out that a good way to construct nice sets of matrices is to use geometry, is to use distance matrices. So let me let me start with a version based on L1 metrics, based on the Banach space L1. If I have endpoints 1 through n, and I have a map from those endpoints to some metric space y, I define d sub f, the induced distance of that function, to be dfij is the distance between f of I and f of j. If that target space is the Banach space L1, these are L1 metrics, and I can define K1 to be the set of L1 metrics on the points 1 through n. So these are the sets of distance matrices induced by an embedding into L1. Then, by a result of lineal London and Rabinovich, the minimum over the L1 metrics is the same as the minimum over the cut metrics, basically because every L1 metric, every metric induced by such an embedding, is a linear combination of cut metrics. So if you have a L1 metric that minimizes sparsity, then you can decompose it into a sum of cut metrics, and one of those cut metrics is going to be equally sparse. So on one hand, this gives us, so we see this tension again. This is very close to a solution. This is the minimum over K1 is the same as the minimum over C, but the corollary of that is that, well, if it's hard to find the minimum over C, it's going to be equally hard to find the minimum over K1. So this doesn't quite give us a nice approximation because it's just equally hard to compute. We can get something better, but this gives us an idea of how to get something better. Namely, instead of just considering maps to L1, let's consider all possible distance functions on endpoints, all possible endpoint metric spaces. Then we get a set of distance matrices M, and you can show that, and this is a theorem of lineal London and Rabinovich and Oman and Rabbani, you can show that the minimum over all the distance matrices is within a factor of log n of the minimum over the cut metrics. And the reason for this is because arbitrary metric spaces are about logarithmically far away from cut metrics, from linear, from the theorem of Bourgain, that every endpoint metric space embeds in L1 with logarithmic amount of distortion. And so if you have a distance matrix that minimizes sparsity, then you can approximate it by an L1 metric, and you can take that L1 metric and you can approximate it as a sum of cut metrics. So this is within log of the actual solution to the sparsest cut problem. How can we do better? Well, instead, so we can maybe do better if we can find some subset of the distance matrices that contains all the L1 metrics. One subset like that, yeah, and furthermore, the minimum over all the metrics can be calculated in polynomial time by linear programming. How can we do better? Well, we want to find some subset of the set of distance matrices that contains the L1 metrics, and so we can still calculate the minimum over that set in polynomial time. One good set is what's called the, one way of doing this is what's called the Goemon's lineal relaxation. This is based on taking a minimum over not all the distance matrices, but all the distance matrices with negative type. The definition of negative type is not really crucial here. What it means is that the n by n distance matrix is negative definite on the complement of the all ones vector, on the orthogonal complement of the all ones vector, but we're really not going to use that definition. The one thing we are going to use about this is that all cut metrics have this property. Every cut metric has negative type. So the negative type metrics contain the cut metrics, are contained in the set of all distance matrices, and therefore the minimum over the negative type matrices is less than or equal to the minimum over the cut metrics, but it's at least as good as the minimum over all the metrics. And furthermore, because of this definition in terms of negative definiteness, that minimum can be computed in polynomial time. So this is also computable in polynomial time, and it's at least as good as the relaxation over all metric spaces. That raises the question, well, is it better than the minimizing over all metrics? And it turns out the answer is yes. We can define a function which measures how good a relaxation like this is, the integrality gap. The Goemon's lineal integrality gap is alpha of n is the maximum ratio of phi CD over phi n CD, where C and D are n by n matrices, symmetric, non-negative entries. We know that phi CD is always greater than or equal to phi n CD, so this is always greater than or equal to 1, and smaller is better. Smaller would mean that it's a better approximation. Aurora, Lee, and Noor showed that alpha of n is bounded by log n to the power of 1/2 plus something that's little o of 1. So in particular, this is better than the integrality gap for minimizing over all metrics by at least a factor of root log n. And for a long time it was open whether alpha of n is bounded, whether this integrality gap is bounded. Equivalently, because of this metric characterization, alpha of n being bounded would be the same as every finite negative type metric space embedding in L1 by a bi-Lipschitz map. This question was answered first by Cote and Vishnoi, who showed that alpha of n is at least log n to a power. I think the power they showed was 1/6. This bound was improved by Tiger, Kleiner, and Noor, who showed that alpha of n is at least log n to a power. Unfortunately, the power that they found was extremely small, was on the order of 2 to the minus 60 or so. But this example was based on the Heisenberg group. And then more recently with Asaf Noor, Asaf Noor and I have found the sharp exponent here, have shown that 1/2 is actually sharp here. We showed that there is an endpoint subspace X of the Heisenberg group H5, such that any embedding of X into L1 has distortion at least on the order of root log n, and therefore that the integrality gap of the Goemon's lineal relaxation is at least on the order of root log n. It's okay so far? So this is the computer science background. This is the problem that got us interested in looking at embeddings of the Heisenberg group in L1. And let me just take a moment. And if you came in late, the slides here are online at, this URL. Okay. So that's the computer science. Now let's get into the geometry. Like I said, this bound is based on the Heisenberg group. So let's talk about the Heisenberg group. So the Heisenberg group is a nilpotent Lie group. The 2k plus 1 dimensional Heisenberg group is a subset of the k plus 2 by k plus 2 matrices, which is a 2k plus 1 dimensional nilpotent Lie group consisting of matrices that are upper triangular with ones along the diagonal, non-zero entries along the top row, non-zero entries along the rightmost column, and all the entries are real numbers. So this is 2k plus 1 dimensions. This contains a lattice, which we denote hz. This consists of all the entries where all the matrices like this, where all the coefficients are integers. And that lattice is generated by 2k plus 1 generators, x1 through xk, y1 through yk, and z, where x1 is the matrix with a 1 in the x1 position and zeros everywhere else. Y1 is the same thing, 1 in the y1 position, zeros everywhere else, and so on. Such that these matrices, if you do the matrix multiplication, you can show that the commutator of x sub I and y sub I is z, and all the other pairs commute. In particular, the subgroup generated by Z is the center of this nilpotent group. This is the algebraic definition of the group, but we can also do, but for our purposes, we really want to put a metric on it. We really want to get to talk about its geometry. So how do we put a metric on this? Well, the easiest way to put a metric on this is to look at the Cayley graph of the group. So this is the Cayley graph of the lattice in the three-dimensional Heisenberg group. The Cayley graph of a group is a graph where the vertices of the graph correspond to the elements of the group. In this case, our lattice is in bijection with Z3, is in bijection with the lattice points in R3. So I've just drawn the vertices as lattice points in R3. And you can check that if you take a upper triangular matrix like this and multiply by x, it increases the x coordinate by 1. If you multiply by z, it increases the z coordinate by 1. If you multiply by y, it increases the y coordinate by 1, and it increases the z coordinate by the x coordinate. So as we go from left to right, the x coordinate grows, and so these lines going back, these edges going back, tilt more and more steeply as you go from left to right. And if I were to extend this the other way, they'd start tilting downward. Now, the relations from the previous slide, that the commutator of x and y is z, and that any other pair of generators commute, those show up in this graph because you can see that if you start at any point and you move x, z, x inverse, z inverse, you come back to where you started. If you start at any point, you go y, z, y inverse, z inverse, you come back to where you started. And if you start at any point and you move x, y, x inverse, y inverse, that's the commutator of x and y, you end up one step above where you started. The commutator of x and y is equal to z. And these spirals have a strong influence on the geometry of the graph because, well, for one thing, they appear everywhere in this graph. So here's one of these spirals. We have a bigger one like this, x squared, y squared, x to the minus 2, y to the minus 2 is equal to z to the 1, 2, 3, 4. We can draw a bigger one like so. In this case, x to the fourth, y to the fourth, x to the minus 4, y to the minus 4 is z to the 16. And more generally, x to the n, y to the n, x to the minus n, y to the minus n is z to the n squared. Going around a spiral, taking 4n steps in a spiral pattern is the same as taking n squared steps going up and down. So these spirals, like I said, have a strong influence on the geometry. One way to see that is that these spirals are all scalings of one another, for one thing. If I take this spiral here and I stretch the x coordinate by a factor of 2 and the y coordinate by a factor of 2 and the z coordinate by a factor of 4, I get this spiral here. If I do the same thing again, if I squash the x coordinate by 2 and I scale the y coordinate by 2 and the z coordinate by 4, I get this picture here. And more generally, if I multiply the x coordinate by n, the y coordinate by n, and the z coordinate by n squared, that's an automorphism of the group, which corresponds to a sort of scaling of the graph. So that's one way these affect the geometry. Another way is that because of this equation, because going 4n steps around a spiral is the same as moving n squared steps vertically, That means that if you want to move a long distance vertically, the most efficient way to do that is to take a big spiral. And furthermore, if I have 2 points in the graph that are far apart, and I want to connect them by a shortest path, the shortest path from here to here has to be, the shortest path from here to here has to be mostly made up of horizontal edges, of red and blue edges, of X and Y edges. Because if I have a path from here to here that contains a lot of vertical edges, then I could take those vertical edges and replace them with one big spiral. I could make the path shorter. And so there's a limit, there's a bound on the number of vertical edges that can be in a shortest path. Okay? So this tells you about what happens for the lattice. We're really interested in what happens in the Lie group. So how can you pass from the lattice to the Lie group? Well, if we keep on doing this scaling, if we keep on, scaling the x coordinate by n and the y coordinate by n and the z coordinate by n squared, we're going to get graphs like this to get more and more dense. And so we can take the metrics on those graphs and take a limit to get a metric on the entire Lie group. And that metric on the entire Lie group is going to be a pretty nice metric, because on one hand, it's going to have a scaling. It's going to have an n by n by n squared scaling. And on the other hand, shortest paths in the graph only have boundedly many vertical edges. So if we take this scaling limit, those boundedly many vertical edges have to get shorter and shorter. Their length has to go to 0. And so in the limit, shortest paths in the limit can have no vertical edges because those vertical segments get shorter and shorter. In fact, what you have is you have a metric space where you can only really move in, where you have a 3-dimensional space where you can only move in 2 directions at any given point. You have something called a sub-Riemannian metric. A sub-Riemannian metric is like a Riemannian metric, except that except some vectors can have infinite length. At each point, you have some, in this case, a 2-dimensional subspace of vectors that have finite length. That's called the horizontal vector space. And for the Heisenberg group, that horizontal vector space is the vector space that's spanned by these red and blue edges. So you can see in this picture here, these horizontal vector spaces start to tilt as we go from left to right. Going along with that, we define a curve to be horizontal if it's always tangent to these horizontal vector spaces. Horizontal curves are going to be the curves that have finite length. They're going to be the curves where the length is defined by the metric. And so we define the distance between 2 points in the space to be the shortest length of a horizontal curve from U to V. So if I have a point here and a point here, I have a horizontal curve going from here to here of length 1 between those 2 points. But if I have 2 points that are separated vertically, the vertical line between them is not a horizontal curve. If I want to move vertically, I have to move around one of these spirals. So the distance from here to here is roughly, the length of that spiral. This has a bunch of nice properties. On one hand, the scaling, the n by n squared scaling that we saw in the lattice carries over to this sub-Riemannian metric, multiplying the x coordinate by t, the y coordinate by t, the z coordinate by t squared scales the metric by a factor of t. You can check that if you take this picture and you scale by t by t by t squared, then it takes this horizontal distribution into itself. And so it takes horizontal curves to horizontal curves. It multiplies length by a factor of t. Because of that, the ball of radius epsilon is approximately an epsilon by epsilon by epsilon squared box, because it's the epsilon scaling of the ball of radius 1. And if you scale the ball of radius 1 by a factor of epsilon, epsilon, epsilon squared, you get something that's roughly epsilon by epsilon by epsilon squared. Consequently, all of these vertical curves, all these black lines in this figure, all of these have Hausdorff dimension 2. Because if I want to cover this segment by balls of radius epsilon, it's going to take roughly epsilon to the minus 2 of them. And so each of these vertical lines has Hausdorff dimension 2. Okay, so this is the Heisenberg group. What does this have to do with the Goleman's lineal relaxation, with the sparsest cut problem? Well, remember, we said that the accuracy of the Goleman's lineal relaxation depends on how well negative type metric spaces embed in the Banach space L1. The Heisenberg group turns out to be bi-Lipschitz equivalent to a negative type metric space. The sub-Riemannian metric on the Heisenberg group is bi-Lipschitz equivalent to a metric of negative type. And Cheeger and Kleiner showed that there is no bi-Lipschitz embedding from a ball in the Heisenberg group to L1. Consequently, finite subsets of the Heisenberg group do not embed in L1 with a uniform bi-Lipschitz constant. Because if they did, if you could embed any finite subset of the Heisenberg group uniformly in L1, then you could take the unit ball, you could take denser and denser subsets of the unit ball, take embeddings of those subsets in L1, and they would converge to a bi-Lipschitz embedding of the unit ball, which by Cheeger and Kleiner does not exist. So the connection between the Heisenberg group and Goemon's lineal is that this is an example of a negative type metric that embeds particularly poorly in L1. Is this okay so far? Are there any questions about any of this so far? Okay. So why does this embed so poorly in L1? Yeah, so this provides counterexamples to the Goemon's lineal question. Why does this embed so poorly in L1? Well, one reason is that it just generally embeds poorly in vector spaces, period. There's a theorem of Ponceau and Semmes that there is no bi-Lipschitz embedding from the Heisenberg group to Euclidean space Rn. And this is based on a theorem of Ponceau that every Lipschitz map from the Heisenberg group to Rn is what's called Ponceau differentiable almost everywhere. That means ordinarily, if I have a map from Rm to Rn, differentiability means that that map can be approximated by a linear map on sufficiently small balls. Ponceau differentiability is very similar. On sufficiently small scales, this map is close to not just a linear map, but actually a homomorphism from the Heisenberg group to Rn. But because the Heisenberg group is non-abelian and Rn is abelian, you can't construct very good homomorphisms. Any homomorphism has to send Z to 0. And so any Lipschitz map from the Heisenberg group to Rn has to collapse that vertical direction, has to send those, has to send all those curves of Hausdorff dimension 2. They have to collapse. And so any Lipschitz map to Rn collapses the Z direction, and so it can't be bi-Lipschitz. It's okay.
So can you give us some intuition for why this statement is true about being Ponceau differentiable almost everywhere?
Yeah, I can. Let me. So one way of thinking about this is if you go back to our picture of the Heisenberg group, our Heisenberg group is foliated by these red lines going in one direction and these blue lines going in the other direction, right? So if I have a Lipschitz map from the Heisenberg group, if I have a Lipschitz map from the Heisenberg group to Rn, then I can look at the restriction to one of these lines. This is a Lipschitz map. This is going to be some Lipschitz curve in Rn. And by Rademacher's theorem, we know that a Lipschitz curve in Rn is differentiable almost everywhere. Near almost every point, we can blow up around that point. If we blow up around that point, we get something close to a straight line. With some, so our Heisenberg group is foliated by these straight lines. With a bit of measure theory, you can find a ball in the Heisenberg group so that so that you have differentiability on all of the red lines going through that ball. So that for every one of these red lines going through this ball, they map to something close to a straight line in the Heisenberg group. And by the same sort of measure theory, you can say that every blue line going through that ball does the same thing. Every blue line through that ball maps close to some line. In fact, all the blue lines map close to parallel lines in Rn. And so you can find some ball in the Heisenberg group, which might be very, very small, where all the red lines map to lines going in one direction and all the blue lines map to lines going in another direction. But then you have a problem, because we know that if you start at a point in the Heisenberg group and you go around a spiral, right? If you go x, y, x inverse, y inverse, then you end up separated from where you started. If you go distance r, distance 4r around a spiral, you end up about distance r away from where you started. But if you're inside a ball like this, where all the red lines and all the blue lines map to parallel lines in r, then the image of that spiral is going to go around a parallelogram. It's going to follow a red line, then a blue line, then a red line, and then a blue line, and it'll be basically back where it started. So So Ponceau's theorem here is really relies on Rademacher's theorem. Rademacher's theorem tells you that that you can find some ball where all the red lines in that ball map to parallel lines in Rn, all the blue lines in that ball map to parallel lines in Rn, and that's a problem because that means that spirals map to parallelograms. That means that points that are vertically separated in the Heisenberg group get collapsed by this map. Does that make sense?
Yeah, thank you.
Sure. So any homomorphism sends z to 0, so any Lipschitz map has to collapse the z direction, like the picture. And this applies fairly generally. Krieger and Kleiner noted that this doesn't just work for Rn, this actually works for any vector space with the Radon-Nikodym property, which includes all the LP spaces where P is greater than 1, less than infinity. But it does not include L1 itself, because that because Ponceau's theorem doesn't work in L1, really because Rademacher's theorem doesn't work in L1. This argument about the blue lines and the red lines really relied on the fact that a Lipschitz curve in Rn has to be differentiable almost everywhere. It has to be close to a straight line almost everywhere. But that's not true in L1. The standard example is this map. F is a map from the unit interval to the set of L1 functions on the unit interval, where F sends t to the characteristic function of the interval from 0 to t. You can check that this is an isometric embedding, but it's not differentiable anywhere. It can never be approximated by a linear map. And so you can't apply Ponceau's theorem in L1. Regardless, you can still show that the Heisenberg group does not embed in L1. This is Krieger and Kleiner showed that there's no bi-Lipschitz embedding from the Heisenberg group to L1 using a version of differentiability based on cut metrics. So remember we talked about cut metrics earlier, and one of the things we said about cut metrics is that every L1 metric on a ball or on any metric space is a linear combination of cut metrics. Specifically, we can write this. If F is a map from the unit ball to L1, then there is a measure on the power set of the unit ball such that the distance between f of x and f of y is the integral over mu with respect to mu of the cut metrics d sub s. So we can write any L1 metric on B as a combination of cut metrics. Consequently, if we want to think about maps from the Heisenberg group to L1, it's enough to think about cuts in H2k plus 1 in the Heisenberg group, in the domain. Furthermore, we don't have to consider arbitrary cuts. We don't have to consider arbitrary subsets. I need a little bit of notation. Open sets in the Heisenberg group have Hausdorff dimension 2k plus 2. That's because all these vertical lines have Hausdorff dimension 2. So a lot of things have Hausdorff dimension 1 more than what you would want, what you would expect. So open sets have Hausdorff dimension 2k plus 2. Any surface that separates two open sets has Hausdorff dimension at least 2k plus 1. And so we're going to define area to be 2k plus 1 dimensional Hausdorff measure. Volume is 2k plus 2 dimensional Hausdorff measure. And then we can state the following. If we have a Lipschitz map from the ball to L1, then the corresponding cut measure is supported on finite perimeter sets, on sets where the area of the boundary is finite. And furthermore, the total area of the boundary of those sets is bounded by the Lipschitz constant of the map. Because remember, we're saying that the distance between f of x and f of y is bounded by the measure of the set of cuts that separate x and y. So if our map is Lipschitz, that means that 2 points that are close together can't be separated by too many cuts. That means that the boundary of these cuts can't be too big. And this is the inequality, that all the cuts have to be finite perimeter, and the total of that perimeter is bounded by the Lipschitz constant of the map. Consequently, so we've reduced from Lipschitz maps to L1 to cuts of the Heisenberg group to finite perimeter cuts of the Heisenberg group. And that lets us apply theorems about finite perimeter subsets of the Heisenberg group. For instance, Franchi, Serapioni, and Seracasano showed that if you have a finite perimeter subset of the Heisenberg group, then it is rectifiable in the sense that near almost every point in the boundary is close to a plane containing the z-axis. The set has a tangent plane, and that tangent plane is vertical. Consequently, what Heeger and Kleiner show is they use a little bit of measure theory to show that for almost every point in the domain of your map, there is a small ball around that point, such that most of the cuts through that small ball are close to vertical planes. If they were exactly vertical planes, then, well, if one of your cuts is a vertical plane, then any 2 points that are separated vertically are on one side or the other side of that cut. So if all your cuts are vertical planes, then that means that the distance between the images of two vertically separated points is 0. A map where all the cuts are exactly vertical is constant on vertical lines. A map where most of the cuts are close to vertical is close to a map which is constant on vertical lines. But constant on vertical lines means that it collapses pairs of vertically separated points. It means that it's not by Lipschitz, and so any map like this is not by Lipschitz. So they go from Lipschitz maps to L1 to cuts to finite perimeter cuts, and then they use a rectifiability result about finite perimeter cuts to prove a differentiability result for those Lipschitz maps. Is this okay so far? So this is non-quantitative. This tells you that there's some ball where vertical lines collapse, but it doesn't tell you much more than that. If you do this argument carefully, Heeger, Kleiner, and Noor went through this result and tried to figure out exactly how big that ball, where all the vertical lines collapse, exactly how big that ball is, and they showed the following. If you start with the unit ball, there's some delta greater than 0, such that for any epsilon greater than 0 in any one Lipschitz map, you can find a ball B prime of radius at least epsilon inside the unit ball, such that the restriction of f to that smaller ball is log epsilon to the minus delta close to a map that's constant on vertical lines. So if you want it to be, say, 1/10 close to a map that's constant on vertical lines, this tells you how small you have to take. You might have to take that ball in order to get that closeness. And on the one hand, and that's good because this gives you a nice quantitative bound on distortion. It gives you a bound that alpha of n is at least log n to the delta. On the other hand, this is not completely satisfactory because that delta, the delta that comes out of this argument is extremely small. Is on the order of 2 to the minus 60. So if you want to get a map that's, say, 1/10 close to constant on vertical lines, you need to choose a absolutely ridiculously small epsilon in order to do that. So, but if you remember at the beginning, I said that Asaf and I had proven a sharp exponent on this bound. So how do you go from this tiny 2 to the minus 60 exponent to 1/2? Very roughly speaking, what we do is that this argument finds a ball on which all the vertical lines collapse. This argument finds a ball, a single ball, where the map is close to a map that collapses every pair of vertical lines, every pair of vertically separated points inside that small ball. In order to show non-embedding, that's stronger than what you need in order to show Lipschitz non-embedding. So what we do is we prove a weaker result, sort of an average case result. Instead of trying to find some ball on which all the vertical lines collapse, we try to show that on average, vertical lines collapse on average. That if you pick a random pair of vertically separated points, you can get a pretty good bound on how collapsed that pair of points is. So specifically, what we do is we prove the following inequality. So for k bigger than or equal to 2, if B in the 2k plus 1 dimensional Heisenberg group is the unit ball, and Z is the generator of the center, and F is a Lipschitz map, then the following inequality holds. And there's a bunch of stuff going on in this inequality, so let's just unpack this for a bit. We're integrating from 0 to 1 the integral over B of the distance between f of x and f of xz to the t over the distance between x times x and xz to the t with respect to x. And then we square that and we integrate that from 0 to 1 with respect to dt over t. So let's take this from the inside out. This quotient here, the numerator is the distance between f of x and f of xz to the t. The denominator is the distance between x and xz to the t. So this is sort of how distorted a pair of vertically separated points is. It compares the distance between the image of x and xz to the t with the distance in the domain between x and xz to the t. Then we integrate that over x as x ranges through the ball. So this is the average distortion of a pair of points that are separated vertically by t inside the ball. And then we square that average. Then so that deals with points that are separated by t vertically. We really want to look at all possible separations of all possible separation distances. So we're going to integrate t from 0 to 1. And we're going to integrate with respect to dt over t because that means that every scale counts roughly equally. So the scale from distances between 1/2 and 1 count just as much as distances between 1/2 and 1/4, as much as 1/4 and 1/8, and so on and so forth. So this is really the average distortion of the average separation of two vertically separated points over some particular distribution of vertically separated points in the ball. And this inequality says that this is bounded in terms of the Lipschitz constant of the map. This leads pretty quickly to a proof that the ball does not embed bi-Lipschitzly in L1. Because if you could find a bi-Lipschitz embedding, then this quotient would always be bounded away from 0. So the average of this quotient would be bounded away from 0. And if you integrate from 0 to 1 dt over t, something bounded away from 0, you get infinity. So if f were bi-Lipschitz, this integral would be infinite. So we can conclude that the ball does not embed bi-Lipschitzly in L1. But in fact, we can use this to get sharp bounds on the distortion. Because if I take the ball of radius r in the integer Heisenberg group, then that also has to satisfy a bound like this. In fact, if I have an embedding of the ball of radius r in the lattice, then distances in that ball range from 1 to r. And so instead of integrating from 0 to 1, we can write this integral as an integral from 1 to r. And again, if you have a bi-Lipschitz map, then this is bounded away from 0. If you integrate some constant from 1 to r with respect to dt over t, you'll pick up a log r. And so you end up with a root log bound on the distortion of that map of the ball of radius r. Is this okay so far? Okay. So, okay, I got 10 minutes left. So how do you prove this? Well, the proof of this follows a similar strategy to the proof of Cheeger and Kleiner. Remember, in Cheeger and Kleiner, you start with a Lipschitz map, you turn it into finite perimeter cuts, and then you bound the finite perimeter cuts. Here we do the same sort of thing. We can go from a Lipschitz map to an inequality about cuts. So if S is a set with finite perimeter, let's define the symmetric difference operator. S symmetric difference T is a set of points that are in S but not T, or in T but not S. And this inequality on the Lipschitz distortion is equivalent to this inequality about cuts. That the integral from 0 to infinity of, again, let's unpack this. In the middle here, we have the volume of S symmetric difference SZ to the T. That's the amount that the set changes when you translate it up by T. Equivalently, that's the number of points that are separated vertically by t, such that one of them is inside the set and one of them is outside the set. So this quotient here is very similar to the quotient we saw before. This measures how well points that are separated vertically by t get separated by the map. And so again, we take an L2 norm of this and we integrate with respect to dt over t. So on one hand, this inequality is very similar to the previous inequality because this is very closely related to Lipschitz distortion. On the other hand, this inequality can be read as an inequality about the shape of finite perimeter sets in the Heisenberg group. It's an inequality about how vertical a finite perimeter set in the Heisenberg group is. Because if S is exactly vertical, if S is a union of vertical lines, then it's invariant under multiplication by z to the t, which means that this numerator is 0, which means that this whole inequality would be 0. And if you want to make S, if you want to increase the left side of this inequality, what do? Well, you take that vertical set and you add bumps to it. You take that vertical set and you add maybe a bump going like that. But if you do that, and so that means that if you translate, then the bump moves up and down, the set changes. But on the other hand, if you do that, if you start making your set, instead of vertical, if you start making it bumpy, this left side increases, but the inequality says that the right side has to also increase. So this inequality tells you that if you start making a set bumpy, then the area has to increase. So how do we prove this? Well, we use a version of rectifiability. So remember, Cheeger, Kleiner, and North's argument used rectifiability to prove a sort of differentiability. They showed that surfaces in the Heisenberg group are rectifiable, which means they have vertical tangent planes almost everywhere, which means that maps to L1 are differentiable in the sense that at sufficiently small scales, vertical lines collapse. This is really an infinitesimal argument. This is really dealing with sufficiently small scales. We want to prove something similar. Instead of showing that surfaces in the Heisenberg group are close to vertical at very small scales, we want to prove that on average, surfaces in the Heisenberg group are close to vertical planes. So we want a sort of average case version of rectifiability. And there is an average case version of rectifiability. It's called uniform rectifiability. The way that I like to think about uniform rectifiability is that it is, well, let me draw a picture. So rectifiability, like I said, is really an infinitesimal phenomenon. So if you construct a set, you can make it rectifiable, but it can also be a very complicated set. The standard example is the Koch snowflake. So if I do the Koch snowflake, I start with a line, I add an equilateral triangle, and then triangles on the sides of that, and then triangles on the sides of that, and so on. The Koch snowflake, the limit of this construction is not rectifiable. The limit of this is not a rectifiable curve, but if I just do this construction, if I add these triangles, say for 100 iterations, that curve is rectifiable. That curve is rectifiable because it's made up of, 4 to the 100 tiny little straight line segments, and that's rectifiable. But it's not really uniformly rectifiable. It's not really, it's close to a plane on very, very small balls, but it's far away from a plane on larger balls. And uniform rectifiability captures that notion. It captures the notion that a set is reasonably close to a plane on most balls. The definitions are a little bit complicated. One definition is that a set is uniformly rectifiable if and only if it has what's known as a corona decomposition. Very roughly speaking, that means that for most balls, all but a few balls B, the intersection of B with the set is close to the graph of a Lipschitz function with small Lipschitz constant. The standard example is the square. The square is uniformly rectifiable because I can draw 4 Lipschitz graphs, 1, 2, 3, 4, one for each side of the square, so that if I look at most balls, any ball that doesn't contain one of the corners of the square, the intersection of the set with that ball is close to one of those Lipschitz graphs. This can be generalized to the Heisenberg group. This can be generalized to the Heisenberg group. And so we prove our inequality in the Heisenberg group by proving a decomposition result. We prove that surfaces in the Heisenberg group are made of uniformly rectifiable pieces like this. This is based on a similar theorem in Euclidean space, that if you have some object in Euclidean space, no matter how complicated it is, you can break it down into uniformly rectifiable pieces. In this case, you can take that Koch snowflake and you can write it as a sum of all these little triangles, and all these little triangles are in fact uniformly rectifiable. There's a version of this in the Heisenberg group, which says that a subset of the Heisenberg group can be decomposed into pieces so that each piece has a corona decomposition that doesn't approximate by Lipschitz graphs, because that's not a reasonable notion in the Heisenberg group, but that approximates by what are called intrinsic Lipschitz graphs. Again, I'm out of time to give full definitions, but an intrinsic Lipschitz graph, an example of an intrinsic Lipschitz graph looks like this. This is a surface where like a Lipschitz graph, it varies relatively slowly, but because we're in the Heisenberg group, because we have this difference between horizontal directions and vertical directions in the Heisenberg group, the intrinsic Lipschitz condition is very different in horizontal and vertical directions. If you move in horizontal directions, like along this ridge or along this valley, the function varies relatively slowly. But if you move in vertical directions, the function is going to vary very rapidly. Nevertheless, you can prove bounds on the behavior of these functions. You can use representation theory of the Heisenberg group to show that if k is greater than or equal to 2, then intrinsic Lipschitz graphs can't be too rough. They have to satisfy an inequality like this. This is the inequality you wanted to show for arbitrary surfaces, and it holds for intrinsic Lipschitz graphs, but arbitrary surfaces can be decomposed into first uniformly rectifiable sets and then into intrinsic Lipschitz graphs. And so therefore, this holds for arbitrary sets, and that gives us the bound that we want on embeddings of the Heisenberg group into L1. Is this okay so far? I have one more slide just to because a lot of these results are from a couple years ago. I just want to update you on what's happened more recently. The main thing, so recently, it's often I have been working on a project. It's on the archive to show that, well, all these inequalities. Somewhere in the middle of the talk, I started adding the assumption that k is greater than or equal to 2, that we're dealing with the Heisenberg group of dimension at least 5. That turns out to be crucial. If all these inequalities work in 5 dimensions and up, but they don't work in 3 dimensions. Surfaces in the Heisenberg group of 3 dimensions can be much bumpier than surfaces in the 5-dimensional Heisenberg group. And the ball of radius r in the 3-dimensional Heisenberg group embeds much more nicely in L1 than the ball of radius r in the 5-dimensional Heisenberg group. And we actually use this to construct a metric space that embeds bilipschitsly in L1 and L4, but not LP, for p between 1 and 4, which is the first example like that we know of. And then one further development, which is, well, I guess this is more of an open question. In doing this, so uniform rectifiability in RK, part of the reason it's so useful is that there are a lot of different ways to define it. You can define it in terms of singular integrals, what are called beta coefficients, these corona decompositions, something called the big pieces of Lipschitz graph property, and many, many more definitions. We've been using one of those definitions. We've been using corona decompositions to study a class of surfaces in the Heisenberg group. Do the other definitions also generalize? Can we also get a good notion of uniform rectifiability in the Heisenberg group? Okay, thanks.
That's great. Thank you very much. Very, very interesting collection of ideas. Are there any questions?
I have a question. So does this imply that in H1 you don't have uniform rectifiability?
Well, Okay, so this is the project I'm working on at the moment, and we haven't actually proved we don't actually have a proof, but we're working on it. We suspect that we suspect that you can so in RN there's sort of a unique notion of uniform rectifiability in that all these definitions all connect, they're all equivalent to one another. We suspect that at least in H1, there may be more disconnections between these definitions. We think we have an example. This is work with Vasilis Trusionis and Sean Lee that is in progress, but we suspect we have an example of an intrinsic Lipschitz graph where singular integrals behave badly.
So the problem is not on the decomposition in Lipschitz graphs, but it's in the estimate that you were showing on Lipschitz graphs.
Yeah. So like in the Heisenberg, so in RN, I mean, a lot of uniform rectifiability definitions are really L2 inequalities, but this construction, this construction of a metric space that embeds by Lipschitzly that correspond in L1 and L4, but not LP, that corresponds to constructing a surface that sort of satisfies an L4 inequality on how bumpy it is. And so it seems like there's a difference between, like in RN, Lipschitz graphs satisfy nice L2 inequalities. That seems like it might not be true in the 3-dimensional Heisenberg group, but it might be true in the 5-dimensional NL Heisenberg group.
So, can you go back one or two slides? So, are you implying that? Yeah. Okay. So, can you go to the next slide? So, are you implying that the first theorem actually does need k bigger or equal than 2 already?
Yeah. So this is actually the result that needs k bigger than or equal to 2.
Okay. I understand.
Yeah, the decomposition.
The decomposition is okay.
The decomposition is okay, but so if you look at this picture, this is this idea of the function varying slowly in the horizontal direction and rapidly in the vertical direction. That horizontal direction isn't constant. You can see that it's a little bit sloped downward over here. It's more horizontal over here. This is really a nonlinear condition. So the way we prove this theorem is we take this surface and we slice it vertically. We do a vertical slice like that. That produces a Lipschitz function on a lower dimensional Heisenberg group that makes a nonlinear condition into a linear condition. And so once you have a Lipschitz function on a lower dimensional Heisenberg group, you can use representation theory to prove this inequality. The problem is that if you start in H1, there's no lower dimensional Heisenberg group to slice into. If you start in H1, you do this slice, you get a 1/2 Hilbert function on R.
Okay.
This inequality no longer holds.
Okay.
In order to prove the L4 inequality that does hold, this does hold with a 4 here, and I think you need a 3 in the numerator, in the denominator. This does hold with if you change the exponents, but that requires doing some careful analysis to deal with this nonlinear condition.
Okay.
Yes, go ahead.
Robert, I'm curious if you thought there are these other nilpotent groups that are sort of based on the quaternions, like they're the boundary of quaternionic hyperbolic space minus a point. I'm curious, have you thought about what happens for those things?
I have not. I gave a related talk on this on Friday, and someone asked me similar questions at that talk too. I haven't really thought about what happens in other Carnot groups. My guess would be, so the really important thing about the 3-dimensional Heisenberg group here is that, well, I mean, we've seen these pictures with this foliation by red and blue lines. More generally, if I take so if I go to this picture, if I take, say, the YZ plane here, this is foliated by blue lines, and more generally, if I take an arbitrary plane, it's foliated by horizontal lines. That's very special. That seems to be special to the 3-dimensional Heisenberg group, that every codimension 1 subspace is foliated by horizontal lines. Because if you do this in the 5-dimensional Heisenberg group, you have a 4-dimensional, a 4-dimensional distribution of horizontal planes. And when you cut that, you're going to get a 4-dimensional surface with a 3-dimensional distribution. And a 3-dimensional distribution on a 4-dimensional space is generally non-integrable. It's generally not a foliation. So the fact that every codimension 1 surface picks up a foliation from the horizontal distribution rather than just some distribution, that's really important. That's important for this analysis, because if you have a non-integrable distribution rather than a foliation, then these slicing arguments work a lot better, because you slice and then you have a nice you have a nice thing to slice into. So my guess would be, in general, that the Heisenberg group is the nilpotent group that embeds best into L1.
Okay. Thanks.
Sure.
Does this give new bounds for approximate solutions to the sparsest cut problem?
So this tells you that this tells you that the Goemon's lineal algorithm, that there are some instances of the problem where the Goemon's lineal relaxation is going to be is going to have an error of root log n.
Great.
So it gives you lower bounds on the approximate solution.
Are there any other questions? And I'd like to thank the speaker again for a very interesting talk. Thank you very much.